the form of K vector.
Yeah. Oh yeah. So you go in, ideally you design K, and you know what K is going to be ahead of time. In real life, you design part of it and you measure it to check it.
Can you give an example of like a low-pass filter plus an amplifier, or the hard problem?
There's an example in the homework set. What you really do, actually, is you don't operate a point in the right half of the S-plane. You just operate on the imaginary axis. And there's a theorem, in fact, it may be the conformal mapping theorem, I don't remember. Some of you who are more mathematical than me may know which theorem I'm talking about. That says if you run a parameter up the imaginary axis here, then it preserves an orientation once you map it into the K-plane. So all you have to do really is map this line, and this line maps into the boundary. So, and in fact the direction gets preserved. So if you're on this line and going this way, whatever's on your right is in the right half of the S-plane, whatever's in your left is on the left half of the S-plane. Same thing over here. As you travel along this boundary, whatever's on your right hand is something that got mapped from the right half S-plane. Whatever's on your left hand got mapped from something on the left half S-plane. So that's what you do. It's not nearly as computationally intensive as you might think from just looking at the region. Another way of looking at things, and one that physicists are often more fond of using, are Bode plots. And again, this is just something I want you to be exposed to so that when other experimentalists give a talk, you'll know what we're talking about. It's an argot. A Bode plot is just another graphical way of representing exactly the same thing that goes on here. Except in this case, we plot it a different way. Here, this is a two-dimensional plot, and this plots a magnitude and a phase of this K vector, which runs along the boundary of this set. So this is a complex number K of some S there. And this thing has a length and it has an angle. And so what we're going to do here, I'm going to call that angle phi, which is separate from the phase margin, which I called a different symbol, theta. I'm going to plot this quantity and this quantity on two separate axes. Here as a function of omega, because we're running S up the axis. So S then is just equal to I omega on this axis. So this is the same omega. Now I'm going to plot the absolute value of the vector K and its phase. And in fact, physicists love to see the behavior in many decades or many orders of magnitude. So we do a log-log plot of this. And so,
do you usually use a natural log, or is it conventional to use natural logs, or do you usually use base 10?
Doesn't matter.
Doesn't matter.
Sure,
base 10.
It's just what?
Base 10.
Okay. I mean, you've written all that, so.
That's because it requires fewer letters.
It's fine.
There. That's more accurate, but more work. Okay. So the magnitude, as we track along the omega axis, the magnitude of K will get smaller. And this is exactly what I've drawn here. Long K, as omega increases, the magnitude gets smaller. And the phase has to decrease. So the phase does something like that. So this starts out at 0, and it works its way down. This looks like it's maybe minus 60 degrees, minus 90 degrees. The forbidden point, minus 1, has a phase of minus 180. And so what we have to do is we have to plot the forbidden point on this type of graph. I'm going to redraw this to make it easier to do so. So that's 0 degrees, it's minus 180 degrees. So, and then this might be, well, correspond to 1, but it might be, the log of that would be 0. But we'll call this log to the base 10 of 1. Right, unit magnitude. So where this thing crosses the unit circle, that is, where its magnitude, the magnitude of k is equal to 1, this is called the unity gain frequency. And you can see at the unity gain frequency, you can just simply read off the phase margin, theta. And the condition for stability, which we said graphically over here, was that this region would not enclose -1, the forbidden point. We can translate over and say exactly the same thing by saying that at the unity gain frequency, the phase margin, or that is the phase, cannot dip below -180 degrees. It's just a different way of saying the same thing. And this is the condition that we as experimentalists use when we design these single input, single output control loops. And again, this doesn't contain any more information than what the Nyquist diagram did. It's just a different way of looking at it, and it's the conventional way. When an experimentalist throws up an open loop transfer function or a closed loop transfer function, this is how they plot it. They plot it in terms of a Bode plot. And now I promised I would redraw that region here to represent this guy. So we'll do a close-up. Forbidden point, unity gain, unit circle, boundary. That is the map. And whatever omega corresponds to this point on the boundary, this is the unity gain frequency. Omega here. And this is the phase margin, this angle. That is, how far you can tilt this boundary before it swallows the forbidden point, -1. And this was the gain margin here to here. So, now I'd like to point out one thing. There's a theorem, and it's related to the Kramers-Kronig relations. If any of you are familiar with the Kramers-Kronig relations, you may be able to see the connection between this. But there's a theorem that relates the phase of a transfer function, or I should say the maximum phase of any transfer function to the behavior or its scaling in its magnitude. And these are Bode's gain phase relations. And what that says is that in any region where the magnitude of k scales as omega to the, what did I use for a symbol? Something. Omega to the Q. The phase, not the phase margin, but the phase, this guy, has to be less than or equal to Q times 90 degrees. And this is one of the things that we use a lot, is we say, oh, well, if we need so and so much phase margin here, then we'll just simply roll it off according to this frequency dependence. And I'm going to throw this out just as an aside. I'm not going to go talk too much about it in this lecture, but there is one problem in the homework set that looks at this. Okay, so that's the basics of control theory, and that's a preparation for what I'm going to talk about next. Does anybody have any questions before I move on to an actual example from interferometric gravitational wave detection? Nope. Okay. I want to talk real quick now that I've laid the foundations for control theory, I want to talk about one application of control theory that we use all the time, and that is laser frequency stabilization. And I hope to use this as an example of the control theory that I've treated so far. So, if we use a laser to do interferometry for gravitational wave detection, the wavelength of the laser is the yardstick with which we're measuring the distance between masses. So for that measurement to be valid, for us to get any use at all out of using this laser, that wavelength has to be very stable. So whatever else you may have been taught in undergraduate physics are not purely monochromatic things. They don't come out of the box emitting light at a single well-defined frequency. There's noise in lasers. Let me talk a little bit about how a laser works, just to remind you. A laser, remember, is some medium, some lasing medium, enclosed in a Fabry-Perot cavity with some pump acting on it, inversion. And the atoms inside the lasing medium go, one of them will emit, and that'll stimulate the rest of them to emit, and they'll all emit in phase. You get stimulated emission, which sets a resonant condition inside the Fabry-Perot cavity. And this light leaks in front. In an actual laser, it goes through a lens, and then it goes on to be used. Now, there's all kinds of things. The thing that sets the frequency of this laser, or the wavelength of this laser, is a combination of many different things. It's the atomic transition, the wavelength of the atomic transition inside the lasing medium, which is typically very broad. This is not a narrow thing. It has to do with the resonant condition of the Fabry-Perot cavity, which is typically much more narrow than the atomic line width. And it depends on other things. It depends on the index of refraction of the lasing medium and whatnot. And just as the frequency depends on many different parameters, if any of these parameters change or shake, then the frequency or the wavelength of the laser, the light that comes out of the laser, is going to change. So if we have, for example, the temperature of the lasing crystal changes, then the effective length of the cavity will change and the frequency of the light will change. If we have acoustic coupling, if somebody's walking around talking and that shakes the mirrors, then that changes the length of the cavity and it introduces noise into the frequency of the laser. Those are just a few of the noise mechanisms that can affect the laser. But just like the thermostat, we don't really want to calculate heat transfer in your apartment. We want a control system which you can just set. Say, I want the temperature to be 78 degrees here. Well, we can do the same thing with a laser. We say, I want the frequency to be, bang, exactly 1,064 nanometers to a part in 10 to the 6 or whatever. And for that, we need two things. We need a way to act on the laser, change its frequency, and a way to measure its frequency. And then we need a way to couple the two. So how do we act on the laser? Well, we act on the laser typically by putting a piezoelectric transducer on one of the mirrors in the Fabry-Perot cavity. Does everyone know what a piezoelectric transducer is, or do I need to define that? Okay. Does everybody know what piezoelectricity is? That we should be able to start with. Piezoelectric transducer, or PZT.
PZT stands for lead zinc zirconium titanate.
Okay. No, it stands for piezoelectric transducer. Whatever it may have stood for in German, it now stands for piezoelectric transducer. So a piezoelectric crystal is just, of course, is something whose length depends on an applied voltage. And if we glue the other end of this thing to the wall inside the laser housing, and then we apply voltage to it, then we can move this mirror backwards and forwards and change the length of the cavity. So we have a voltage going in here that, by changing the length of the cavity, can act on the frequency of the laser. So this is our actuator. For our sensor, we'll use a Fabry-Perot cavity. And unlike the Fabry-Perot cavity inside the laser, this can be a very stable Fabry-Perot cavity, very quiet Fabry-Perot cavity. This thing can have a fixed length spacer, it can have nothing in between the mirrors, it might be suspended from wires to keep the excitations from people walking around on the ground outside from exciting it. It might be under a vacuum to get rid of acoustic excitations. It might even be cooled. People have taken these things and they have cooled these things down to 4 Kelvin or 2 Kelvin and reduced the thermal excitation, the thermal noise in the cavity itself. But the point is, you can have a cavity whose noise is substantially less than the noise in the laser. So for our treatment here, we're going to assume that this cavity is perfect. And go on from there. And assume this is a perfectly good sensor with no noise, no intrinsic noise in and of itself. So how do we measure the frequency of the laser light? Well, remember what the transmission of a Fabry-Perot cavity looks like as a function of frequency. So transmission as a function of nu, and we'll call nu laser frequency. It's just this area function. So, whose line width is determined by the finesse of the cavity, and whose free spectral range is determined by the length of the cavity. So what we might do is we might take a small beam splitter, put it on the output of the cavity, and tap a small amount of the light and send it into a photodetector. A small amount of the light because we want the rest of the light to use for interferometry, otherwise we wouldn't be stabilizing the system. And we might take the output of this sensor, as a photodetector, and we might run it through an amplifier. I'm going to erase the pump here. And we might have a set point, Y bar. And we might take this and send it into here. And that might be our control system. And what we would be doing is, if our set point were here, call this Y bar, then we would be fixing the system on the side of one of these fringes, so that if the laser frequency increased, then the power falling on the photodiode would increase. The system Okay, it's got a minus sign built into it. It would reduce the laser frequency, push it back down, and bring the system back to its set point. Similarly, if the laser frequency got too small, the power would drop, and the servo would give it a kick and push it back up to its set point. And this is the way laser frequency stabilization was done back in the 70s. This was some of the first techniques that were used. And it works okay. It gets it better than out of the box, but it's got some problems that will affect us if we try and use this as a source for gravitational wave detectors. And the main problem, the one addressed most easily in this lecture, is that it couples amplitude and frequency noise, intensity and frequency noise. So this is all well and good if the only thing that's changing is the frequency of the laser. But if the intensity of the laser changes also, then the transmitted beam, the intensity of the transmitted beam can increase. And even if the laser frequency hasn't changed, then the intensity that the photodiode sees can jump way up. Then the servo, not knowing the difference between an intensity fluctuation and a frequency fluctuation, the servo then corrects it by changing the frequency. And all it does is it holds the power falling on that photodiode constant. And so what we've done here is we've actually introduced frequency noise into the system by coupling this intensity noise back into the frequency. And that's a problem. We need to do better than that. And the conventional way that we do that is that instead of side locking to a transmitted beam, we want to lock to 0 and hold it at 0. So what if we were to do this? Now I'm just going to draw the laser. I'm not concerned with what goes on inside it because we have a control system to take care of that. Now what if I look at the reflected beam instead of the transmitted beam? Well, for a lossless cavity, for a lossless perfectly coupled optimally coupled cavity, the reflection R is just 1 minus, well, essentially 1 minus the transmission. So it looks like this.
So you're assuming identical mirrors?
I'm assuming identical lossless mirrors, that's right. And if we could lock to this point, if we could set things so that there is no reflection off the cavity, then we would have two benefits. Number one, we get all the power through. We haven't tapped any of the power out of the cavity to use for our servo system. We get to use all of the power of the laser in our interferometer, and we've decoupled the system from intensity fluctuations. So if we lock to 0 and the intensity of the laser fluctuates, big deal. Fluctuations in 0 are 0. So you no longer couple to intensity fluctuations. The only problem is, how do you tell the system which way to push the frequency if it changes? So if the frequency goes up, the intensity goes up. If the frequency goes down, the intensity goes up. So there's no sign here that can tell the system using this kind of naive feedback circuit, naive sensing system. There's no way for the system to tell which way it has to push the frequency to bring it back on resonance. So what we're going to do is we're going to modulate the laser frequency. And I'm going to draw a close-up of this here. This is a laser frequency. So we're going to modulate the laser frequency and try and measure the derivative of the reflected power. So we'd like to operate on this point. But say we're a little bit off this point. And let's say the frequency at which we operate gets modulated, dithered back and forth sinusoidally at a nice regular signal. Then if the frequency moves up, then what comes out of the system, what goes into the photodiode, does this. As the frequency gets increased, the reflected power increases. As the frequency decreases, the reflected power decreases. On the other side, it's the other way around. Over here, if I increase the frequency here, then the reflected power goes down. So there's a sign change between here and here in the change in reflected power versus the change in the laser frequency. And so if I can measure the output of this photodetector and compare it with the drive that I'm using to change the laser frequency in a phase-sensitive way, then I can measure the derivative of this curve, and I can tell which side of resonance I'm on. And I do this by comparing the signal. Let's see, I've got a diagram here I need to follow. So I've got some sort of an oscillator here that modulates the laser frequency. And then I've got some photodetector that measures what comes out of the cavity, what gets reflected off the cavity. And I need to send the two together into something that I can use to compare them. And I'm going to use a mixer. A mixer is just a circuit element that multiplies two signals. That's it. So in this case, when the frequency is high, let me write down the separate cases here. In this case, when the frequency is high, let's see. In phase, we can write R and nu like this. The product of these two sine waves is positive. It's greater than 0. And that tells us that the frequency is too high. And that should tell the control system to push the frequency down. Similarly, if we are 180 degrees out of phase, so that's one case. If we are 180 degrees out of phase, then R looks like that, but nu looks like that, and the output or the product is negative. The product of these two sine waves is negative. And that implies that the frequency, can everybody see this way down here in the corner? Or is this a problem? So this is case number 2. And so we can go back here and we can modify this. So let's say we've got an oscillator here, summing junction, something that acts on the laser frequency. Mixer. Now, I've drawn here using the same actuator to both modulate the laser frequency and correct the laser frequency. And Shanti, if you're awake, you'll say, this is not what we really do, and that's right. This is not what we really do. There's a much easier way to do this in real life, which actually makes the math easier too, but I'm not going to go through the math. Remember, just like the thermostat, we don't really care about how the details are taken care of at this level. We want to build a control system that makes the thing sit in a state we want it in. And so I don't really care for this treatment, for this lecture, how we're modulating the laser. In some of the reading that you'll do, you may go on and understand how the laser is modulated and exactly how this error signal is extracted. But for now, let's just assume that we are modulating the laser and we can extract an error signal. And let's talk about the control topology of it.
Can we just understand the diagram?
Yeah.
A little bit more.
Sure.
So your oscillating voltage puts out the same signal in both directions.
That's right. It puts out the same signal in both directions. And
then just trace where each signal goes.
okay, so this is the oscillating signal. The oscillating signal goes in here and modulates the laser frequency. Another copy of the oscillating signal goes into the mixer. The output of the Fabry-Pro cavity, that is the reflection off the Fabry-Pro cavity, goes into a photodetector. And the output of that photodetector, which is sinusoidal, at the same frequency that we're modulating the laser frequency at, according to these diagrams. It's at the same frequency, but depending on whether the frequency of the laser is above or below the resonance of the cavity, it might be inverted relative to the frequency drive. And those two go into a mixer and get multiplied. And the output of the mixer, the product of those sine waves, depends on whether this sine is flipped or not relative to this modulation frequency, modulation signal. And then that output, which is either positive or negative, depending on the side of resonance you're on, then goes through some servo amplifier and goes in to act at a lower frequency on the laser.
Now, this type of locking has a name?
Yes, sorry about that. It's named after R.V. Pound, Ron Drever, our own Ron Drever, and Jan Hall. And it was really Drever who came up with the whole idea. Drever came up with the idea specifically for use in gravitational wave detectors, interferometric gravitational wave detectors. It turns out that his postdoc advisor back in the 60s had, in his youth, come up with the same idea for stabilizing microwave cavities. So being the gentleman that Drever is, he gave Pound first credit on the technique, just because it was similar to something that he had invented a long time ago. And Jan Hall was the guy who actually built the first.
Who knew how to build a mixer?
Who knew how to build a mixer. Jan Hall was the guy who, along with Drever and some other people, put together the first really working system with which people seriously studied stability and noise issues. So this technique of modulating the laser frequency and then mixing the modulation signal and the output of the cavity and using that to feed back to the laser is known as Pound-Drever-Hall locking. Ron, you should have caught me on that one. Okay, we have a few more minutes, and I want to assume now that we've constructed a Pound-Drever-Hall lock, and I want to look at it from the standpoint of a controls so most of the underlying physical mechanisms, most of the underlying physical things that go on in this system, we're not too concerned with from a control standpoint, but there is one that's important, and that is the storage time of the cavity. So the cavity doesn't make these frequency measurements instantaneously. It takes a certain amount of time for it to come to equilibrium with the laser light. And I can give you a rough argument for why this is so, and you'll have to trust me on factors of 2 and pi and things like that. So light comes into the cavity and then takes a while to resonate and build up inside the cavity before this reflection curve is established. And that amount of time is approximately a single round trip. So there's a time constant associated with the cavity, tau. And that is equal to the time that it takes the light to go around once in the cavity of length L. And that is just 2L over C times roughly the total number of round trips it makes before it leaks back out. And that's given approximately by the finesse. So this is about the storage time of the cavity. I should say that's approximate, that's not exactly equal. In elementary circuits, some of you may be familiar with these, some of you may not. There's a similar effect that goes on in an RC circuit. Just like it takes time to charge up the cavity with light, it takes time to charge up a capacitor with electric charge. And the behavior of this circuit, if you consider this circuit to be a measurement circuit, where it measures a voltage that goes in by producing a voltage that goes out, the transfer function of this thing is frequency dependent. So V out is equal to V in divided by 1 plus I omega RC. And this thing, if we draw a Bode plot of this, we'll see that it, at low frequencies, below this cutoff frequency, omega C, the output is exactly the input, whereas in high frequencies, the output trails off, and there's a phase lag associated with this. Most of you have probably seen low-pass filter before. Turns out that if you do the math, if you calculate the time response or the dynamic response of a Fabry-Perot cavity, you get exactly the same thing. So the cavity responds with exactly the same frequency dependence as a low-pass filter for low frequencies, for frequencies that we care about. And so if we draw a control system diagram, block diagram, to represent this laser locking system, we can represent the laser by a block. What did I decide to call that? I decided to call that H. H of S, which has units of hertz per volt. That is, you put a voltage in and you get some frequency of the laser light out. And then we have another block, which we'll call the Pound-Drever-Hall block, the sensing method. And this thing will have some sort of a transfer function, D of S, which has units of volts per hertz. So whatever comes out of the mixer there is in volts, and it's proportional to the change in the frequency in hertz between the laser light and the cavity resonance. And then we'll take this out, feed it through an amplifier, K, and have that go back into the laser. So, and if we assume that this one is this transfer function is the only thing that has any frequency dependence, that is, if we assume a perfect laser whose frequency follows the input voltage at all frequencies, and a perfect amplifier, then we can draw a Bode plot of this, and we get exactly the same kind of dependence that we got for the low-pass filter. So in this case, I'm going to draw a Bode plot of the total closed loop, total open loop gain, HDK, and its phase. And again, just like a low-pass filter, up to a frequency that corresponds to roughly 1 over the storage time of the cavity, the system is flat. Above this, the open loop transfer function, that is just the product of each one of these things, falls off as omega to the minus 1. But the phase that it goes down to, let's see, do I still have Bode's gain phase relations? I do. The phase that it goes down to, wherever the magnitude of Any linear system scales as omega to some number. The phase is that number times 90 degrees. Well, here that number is -1. And so the phase limits out at minus 90 degrees. Never gets anywhere near minus 180 degrees. And the boundary that we drew over there for the Nyquist diagrams never approaches the forbidden point, -1, at any time. So this system, admittedly a fairly artificial system, but one that only includes the cavity pole, is unconditionally stable all the time.
You've assumed a perfect amplifier.
Yes.
K is constant.
Yes.
You want to repeat that for the camera?
Kip's pointed out that I have assumed a perfect amplifier. K is constant for all S. And I have also assumed a perfect laser, perfect PZT, where H is constant for all S. Now, in real life, this is not at all the case. In real life, you have resonances in the laser due to the finite speed of sound inside the PZT crystal. You have delays in K, and you have additional, sometimes ringing effects in the cavity itself. And so what you would really have in real life is nice predictable behavior up to the first pole, and then you'd have additional poles and maybe even mechanical resonances at higher frequencies. So in real life, what we do is we introduce a pole in our amplifier at fairly low frequencies, low enough that we suppress all of the gunk that happens at high frequencies, and then we come back and we produce another unconditionally stable servo on purpose. Now, I know I've only got a couple of minutes left, but I want to draw one diagram here and talk about why we did this at all. So, you've seen before in this class the concept of a power spectral density. So there may be some noise in the laser that we want to suppress. And the noise, as a function of frequency, let's say for the sake of argument, is flat. And one of the results that you will prove in the homework is that when the loop gets closed, so in the open loop, if the noise is equal to N, then in the closed loop, that is N as measured using the Pound-Drever-Hall technique, in the closed loop, the noise goes to N divided by the return difference, 1 plus, what were the symbols that I used over there? HDK. And so this is approximately N over HDK when the total loop gain is very large. And the total loop gain is very large, I'm assuming, all the way up to the unity gain frequency. And so if I take this function, this HDK, and plug it in over here to this expression for the noise, so this is the noise N that we had in open loop without any feedback, then I'm simply taking the image of that thing. This is N over HDK. And so below the first pole, whether that pole is the cavity pole intrinsic to the cavity or something that I put in the amplifier, the noise is suppressed by a fairly large factor, this factor of HDK. Above the cavity pole, as the gain of the servo rolls off, the noise comes back up to meet its open loop value. And by the time you get to the unity gain frequency, the servo no longer acts, and the noise at those high frequencies is back to what it was in the open loop. And this is the purpose of the feedback servo. This is the whole reason the Pound-Drever-Hall technique was invented, and exactly what we use it for in interferometric gravitational wave detection. And that's all I had to say.
Thank you.
Any questions? Good.
So, there's a paper by Erik and that I'm putting on the web.
Oh, Ryan, yes.
And Ryan, that you may want to read. It'll be part of the recommended reading. It's available already, and we'll get the problems, maybe the first part of the problem on the web very shortly.